Now, today's presentation is really going to focus upon modular UPS systems, but it's really even deeper than that. It's about applications of UPS and how to use the UPS in today's environment. Things have changed, right? When we look at the marketplace, when you look at the needs, it's been a continually ever-evolving kind of process where the application is slightly different. When I first joined the industry, it was about specs. It was about pouring through. We were really building every UPS system individually to the need and the requirements of the application. Through standardization, optimization, we've really moved that forward, and today it's really about application. It's not about building the inverter to this specification, about building a rectifier to that specification. It's about taking the UPS and how do I use the UPS system in various different applications, various different configurations to optimize the needs of the market. Now, today's presentation, we're going to talk about data centers. It's really a lot of focus, and you're going to see the name data center pop up. And for those of you not familiar or not involved in that space, I apologize up front. It's the largest application of UPSs in power, mission-critical power quality. But the same principles are applied into industrial applications. The same principles that are applied in putting a power solution into a 10,000 square foot, 2 megawatt data center is the same principles being applied into an enclosure for an industrial PLC with a 1 KVA application. When we talk about power quality and we talk about today's systems, we're really going to cover the whole spectrum. We're going to cover the whole gamut because we're going to talk about applications. We're going to talk about drivers that deploy it. The person deploying or the IT technician deploying a 19-inch rack full of 4 or 5 servers is equally as important as the one deploying the data center space, is equally as important to the application as an industrial computer or a PLC on an assembly line type of process. So the needs are very consistent, very similar. And that is around greening, about optimization, improving efficiencies, putting in solutions that can be adapted and expand to future growth. Energy costs, number one factor. There was a time where when we were deploying solutions, we'd look at the IT equipment, we'd look at the computing equipment, which would have a price tag of about $100,000, and that would be the discussion, right? Deploy it, put it in place, deploy the solution, and then we'll worry about the power. We'll put whatever power infrastructure is required behind it because the equipment costs so much. Well, Moore's Law, right? Double the performance at half the price, accelerated 10, 15 years. We're at the point today where that $100,000 of equipment is now only $10,000, $20,000 worth of equipment. But in order to operate, in order to run, in order to sustain, we're going to spend $50,000 on the infrastructure and the energy costs. So the world has now changed to where it's no longer, let's just put it in and we'll worry about the power in the after. Today it's, okay, let's worry about the power up front because that's our number one cost impact. Let's worry about efficiency. Let's worry about green. And this isn't just in the power, it's throughout the entire marketplace in the world we live in today about optimization. Consolidation. I don't know any organization out there that is not consolidating, moving, improving, expanding, integrating, acquiring. All of these business terms really mean the consolidation of equipment, the consolidation of infrastructure, and that's typically the number one cost move from a business perspective. So we're talking about how do we accommodate a power requirement or a power system to accommodate for these changes. What's driving it, right? More efficient power and cooling systems, right? Efficiency, efficiency, efficiency. And what we fail to realize at times is power and cooling are intrinsically tied together. If something is more efficient, it's generating less heat, using less energy, so we have cost savings. But as it generates less heat, I don't need as much cooling, so I got cost savings. On the opposite of that is if it is not efficient and it's consuming all of this energy, it's going to cost me, but it's also creating a lot of heat that I have to pay again to remove. So when we talk about moving power, we're really talking about moving heat as well. And as we move heat around, that becomes an equally important discussion. Now, the purposes today are going to focus upon power, but again, I want you to keep in the back of your mind that the cooling decisions and the cooling discussions follow a very, very similar path. Flexible systems. Things are changing out there. We've got a couple slides coming up where we've done some studies out there and just trying to quantify the magnitude of that change. There is no one solution that solves all enterprises, all businesses, all applications. Everyone is different with a different adversity to risk, a different focus, and a different expansion paths. So what you really need to do is understand individual organizations and create the best solution for them. Higher availability, reliability, pretty consistent out there in that that's why we're here. More and more and more, our dependency upon electronic systems is ever increasing. Therefore, our dependency is there. It just simply cannot afford to go down. And in fact, if you look at the press releases in the newspapers, power outages or operations and enterprises not being operational is always at the top of the page, right? Amazon was down for X amount of time. RIM was down for X amount of time. A year later, and on the drive in, I heard about the outage that RIM had a year ago, still having ripple effects. So what are the costs of these? We simply cannot afford to go down anymore. Equally, when we get into the costs, we get into physical space. I cannot afford to build these large systems. Electrical rooms have gotten smaller. People are putting things in different locations. Space, space, space. Racks, enclosures. Got to try to keep the space down, right? I mean, I have most of my discussions arguing over a 1 inch of gap, 1 inch of space. Just simply don't have the room. Not to mention the cost of this. Data centers, and typically in the computer rooms, it's a very, very costly space. Different locations, again, the cost of space in downtown Toronto is different from downtown New York, which is different from Aurelia, right? So again, those things need to come into play. Scalability. And this is really what we're going to focus on more than anything else, is how to optimize a system. We used to be a time where if you needed a 100 kVA of load application today, I'd say no problem, we'll give you a 500 kVA, right? Oh, you plan a lot of growth? I'll put a megawatt in today, right? Likewise, you have a requirement for 2 kVA, well, you know, you might want to put in a 5 kVA or a 10 kVA for future growth. Oversizing it was not a problem, right? I mean, in fact, I remember when I first joined, you'd flip through a catalog, pick it, and then turn a couple more pages, and that's the power requirement. You oversized everything. It was a great fudge factor. We never exceeded capacity because we just put a whole bunch of it up front. And everyone was doing that. Engineers, consultants, users, suppliers, manufacturers. And in fact, what was often happening was everyone would add 20% along the whole process. We never had to worry about scalability. We never had to worry about this expansion. Well, today, the reality of it is there's a cost associated to oversizing, right? There is an efficiency loss. Any system is really most efficient at 100%. As you go down from there, your efficiency starts to drop. The cost of that solution goes through the roof. So remember, when we talk about the cost of the infrastructure and electrical being 60 to 70% of the overall cost, including the equipment, the IT or the computer equipment, that is a massive amount. So our goal is to minimize that or shrink it as much as possible. And in order to do that, we have to focus upon right-sizing the equipment. Likewise, as things change out there, we need to be flexible. We need to have the ability to change. I asked one of my clients that I have a great relationship, I asked him independently off the record once, I go, how often do things change in your floor? And he said, well, you know, probably I've got about 5 to 10 technicians who come in on a daily basis and move equipment around and move things around. So I said, 5 to 10 every day. He said, yeah, and they could be moving like, you know, a kilowatt here, a kilowatt there. How do you keep track of it all? That's one of his big challenges. As equipment starts moving around, trying to fit the distribution, trying to fit the number of plugs. Another example I have is a Cisco application for a switch. I had a client call me and say, Joe, I'm deploying this switch. What kind of power do I need? And I thought, yeah, okay, I'm not familiar with it, but thank God for Google. Right, quickly typed it in while I had him on the phone, and I'm looking at the specs. Oh, no problem, John, you need a 700 VA UPS, right, 700 VA application. No problem, yeah, it's a little small box. I mean, we can get it. And as I'm talking to him on the phone, I'm scrolling down, and I see this stack-wise technology or a power stack. Well, what it is I can take that one box, and I can add 4 more processors to it, taking it from 700 watts, 700 VA, up to about 1.4 kilowatts. But then I can take 4 of those switches and tie them together. So now I'm up to, potentially, on the order of about 7.2 kilowatts. So I said, John, you better hold off. I don't know what you need. Then I read down on the power cords, and I can have various power cord options. I can have 14 120-volt 15-amp plugs, kind of like our wall plugs, or I can combine them all together and they can operate on a 3-phase power supply if I choose a 3-phase power supply. So all of a sudden now, from a power perspective, I'm sitting there going, well, do I supply a plug-and-play 120-volt 700 VA UPS, or do I need to supply an 8-kilowatt 3-phase UPS? Drastically different. From an electrical infrastructure, right? I mean, do you have 3-phase power? Do you have single-phase power? All the way down to plugs, number of plugs, expansion. So I said, well, hold the fort. We need to go visit the client to figure out what is their ultimate growth and expansion plans. And what do we need to put in place that is both flexible from a power requirement and can grow as they grow, as well as from a distribution to provide the number of plugs that they may eventually grow into. So here's a data to basically substantiate and corroborate the example I gave a couple minutes ago, and that's a dynamic data center. We went out and we surveyed, I think it was about 350 customers of ours or applications, and we asked, how often are you changing, making what's referred to as MACs, right? Modifications, additions, and changes in your data center floor. And what you'll see is if you look at that right-hand column, right here, 42% are doing it several times a week. And this is, again, a slightly dated example. These numbers have increased. What virtualization is kind of an IT perspective towards optimizing server usage and server utilization. What they're saying is, rather than me having 5 servers doing 5 different tasks, all operating at 10% utilization, what they've done in the IT sector is they've said, we're going to create virtualized servers. So there's an email virtualized application or a virtualized server. There's all these virtualized servers for all the applications, and then they're stacking those virtualized applications onto as many servers as they require. So they're taking the 5 servers with physical different applications, and they're now combining them onto one server with 5 virtual or partitions, if you will, onto that one server. Now, the beauty from an IT perspective is those virtual servers can reside on any server anywhere on the enterprise. So they could be on this server, this instant, and literally it comes down to instances, or it can be on this server the next instant. This rack to this rack, this row to that row. Or an organization like Google can move it from the Washington data center to the Seattle data center, and back again. So you have these loads moving around now because of the IT infrastructure and where the enterprise is. And this is becoming more and more prevalent from an applications point of view. Now, we're faced with the challenge of, okay, how do we respond from a power perspective behind that? So when you look at these changes in the dynamics, really change is the only constant in applications. We also asked the same kind of group and we said, how likely are you to purchase a modular approach to this? Gentlemen, in the last piece we were talking, and we got off onto a little bit of a tangent about a large data center rather than putting in a single large UPS, it might be more beneficial to put in 10 small UPSs, one at the end of each row, to get that flexibility. Now I can turn off rows or turn them on and move them around. So this modular approach, and the numbers kind of justify it. When we look at the numbers and we see that a modular approach, somewhat likely or very likely, well over 50% of the applicants. And interestingly enough, it doesn't really matter what the size of the application is. They're all roughly equivalent. So the large data center, the megawatt data center, is looking at the same principles or the same type of need as a smaller data center of 5 racks or 6 racks. Same application, same needs. And really, what's driving this? I want you to draw attention to the red line here. The red line is actually the efficiency of a traditional type of UPS. Very important at 100% load, and that's what all the specs refer to, and that's what we all refer to. At 100% load, we're looking at around 92, 93% efficiency. And it stays and remains that way up to about 50%, 40%, at which point it will start to decay, right? Typically, it's the magnetic losses in the traditional designs that impact that. So there's no load losses that will occur, and they become a bigger part of the overall, and hence the efficiency drop. High efficiency UPSs, really, we're going transformerless. We're increasing the efficiency. So we increase the efficiency from a 93, 92% up to 94, 95%, but at the same time, we maintain it for longer. So when we get into the sweet spot or the typical operating range, we see savings increase from 5% to 10% to 15% at extremely low loads. So ultimately, I want the flexibility of having a system that I can bring on if loads are, and my load requirements increase dynamically or someone changes it, but at the same time, I want to try to operate as close to 100% as possible. So I really want a system that I can optimize for the given load today. And that brings us to a scalable or modular type of system. Now, traditionally, and we've been doing, Exide and Eaton by extension has been doing parallel systems since the 60s and 70s. This isn't new technology utilizing multiple modules. In fact, for the longest time, the largest module out there was only 500 kilowatts, which is pretty big. But when you were building a 4 megawatt system, you would take 8 of these modules and combine them together. In fact, we do it right now on a 3 megawatt system. We don't create a 3 megawatt UPS. You create 3 or 4 1 megawatt UPSs, and you parallel or tie them together. That same concept, that same flexibility is now brought down into even smaller single phase applications, right? If you needed a 6 KVA, I could provide 2, 3 KVAs in parallel to give you that 6 KVA, and then add another one for expansion and build the systems that way. But really, traditionally, fundamentally, in order to get 2 electrical systems, basically 2 inverters, and for purposes, a UPS module is basically incoming power rectified to DC to feed a battery to keep the battery charged, but that DC power is then inverted back to an AC to create clean, filtered, regulated, perfect, guaranteed, 100% pure power to you on the inverter output. When I parallel 2 inverters, I need to really worry about 2 key things. First is they got to be synchronized. They can't be 180 degrees out of phase when I tie them together, or else bad things will happen. And I don't need to go into that detail, right? So they got to be close. They got to be awfully close in order for me not to have a catastrophic event when I tie their 2 outputs together. Secondly, though, in order to load share, they got to be pretty much perfectly in sync. In fact, 1 degree of phase angle difference will result in a 50% load imbalance. So if one of those modules is simply even a 1 degree forward, it's going to take 50% more load than this one. Well, I want them to evenly share the load. So what I used to do before, and the easy way, is I simply tell these 2 inverters, hey, I don't care how you operate, but the control module over here, that's going to tell those inverters how to operate. A system level control module. will tell them how to operate. What's my single point of failure in this system? The control module. So regardless of how reliable, how much money I spend, how much MTBFs I do on the power components, my reliability comes down to the reliability of a printed circuit board or a motherboard. Right? Those of you familiar at all with computers, what fails on a computer? The board, right? Catastrophically, right? The other ones are all little glitches that we kind of get around, but once the board's gone, the whole system is at mercy. So we've been doing this for years with this control module, and we've done all kinds of things to improve the reliability of the control module, but our data shows and had shown us that it still always came down to that single point of failure. So the question was, how do we increase that reliability? How do we increase that performance? How do we increase that means? Well, and we didn't have the choice. When we saw where the marketplace was going, when you see the needs, you have to resolve that single point. So we've taken that technology previously, and again, this is that 3 kVA single-phase application. So we're not talking simply large systems, we're talking small single-phase systems as well, where I have a 3 kVA modules, then I can go a 3, 6, 9. So I can start at 3 kVA and expand up to 18 kVA in 3 kVA increments. I can add redundancy if need be. I can scale forward, I can scale backward. If I look beneath the cover here, the initial designs look something like this. Single input, single output. I've got basically the power modules. They all shared a common battery. They had a bypass, and they had an external control system. The first stage of progress by our design teams was to look at it and say, you know what, we need to start removing single points of failures. That control module is proven to be our single pane. So what we're going to do is we're going to take that single control module and we're going to now put it into each individual module. So each individual component communicates to nobody. It regulates itself independent of the other controls. There's no intermodule communications. How does it do that? Well, remember I said about phase angle, carrying disproportionate amount of load? Each module is continuously trying to carry less load. So in this system where I have 3 modules, each module is continuously trying to carry less load. Each module is continuously phasing back or taking a step back to try to lose some load. Now, if it's a huge discrepancy, then a phase angle will lose a lot of load. But when they're in sync, they're all phasing back the same amount, not losing any load. They are now in sync. And when I say phase back, I'm talking about 3 millionths of a hertz of phase back. And I'm looking at milliamps of output current loss. So I phase back to try. So in a 3-module system such as this, I'm within 5% load sharing within 18 cycles. And then they're pretty much constant. Then there's no deviation. If I lose a module, the other modules have to take the load, right? They don't have a choice in the matter. When I bring on a 3rd module or a 4th module or a 5th module, again, to within 5% load sharing within 18 cycles. Very quickly, they can accommodate. But my advantage here is I have now lost a very significant single point of failure. When we look back at earlier designs of our 3-phase systems, marketed and publicized, we had multiple power modules, be they 10 kVA, 20 kVA, 30 kVA, 50 kVA. We had multiple power modules. However, understanding the control module issue, we put in redundant control modules. But we're still dependent upon a single control network. When we look at single points of failures, we had a single static switch around the entire system. Single DC buses, single DC breakers, single battery systems in a lot of the designs. single control network. This type of an application, this type of a UPS is really a single UPS made up of multiple components. It's not really multiple UPSs. It's a single UPS with some multiple components, with a lot of single points of failures. What we're doing today, and the right way to do it, is to really create it at a system level. What we're doing is we're starting with an input bus, tying them together on an output bus, but then we're putting in 6 individual standalone UPSs into the circuit. Right? They each have their own rectifier inverters. They each have their own battery systems and associated battery breakers. They each have their own static switches. Likewise, their own individual controls and their own maintenance bypass. They are a standalone UPS. In fact, what you can do is you can take a UPS system. Let's say, for example, your organization, your enterprise, your application had 5 buildings, each with their own UPS, operating independently. The initiative has come down from high above. You need to consolidate. We're moving into a new location. You can take those 5 UPSs and simply tie them together into a large power system made up of those 5 UPSs. Be they 100 kVAs, be they 1.1 megawatts, be they 12 kVA applications. The only thing that really changes is the form, function, and the size of the physical size of those UPSs. For the most part, you can tie them all together and create a system like this. This is really a modular power system made up of multiple UPSs. And in fact, if I'm ever building a system, what I really want to focus on is having an A side and a B side that are completely independent. My only tie point is really the output tie bus, is where I need to tie them together. That output tie bus becomes my single point of failure, which is typically a copper bus or a tie mechanism of some sort. We'll see another example in a couple moments. But the goal here is to eliminate all of the single points of failures in building this system. Also, by using standard modules and standard UPSs, it also gives me that level of flexibility where I can separate them at any point in time into standalone systems. So again, by paralleling of these UPSs, I gain that flexibility, gain that scalability, gain the ability of, if I only need 100 kVA, I put in 100 kVA. If I need more power or I need redundancy, I can add a second 100 kVA or a third 100 kVA. Now, maybe the application says, well, you know what, 100 kVA steps, that's awfully lot for us, right? It took us 10 years to get to 100 kVA. I don't think we want to wait another 10 before we can justify that. Okay, that application, maybe the blocks need to be smaller. Maybe I start with 250 kVAs today in a 100 kVA application, and then I can add another 50. So now my steps are 50 kVA steps. Maybe I want to look at 12 kVA steps. Again, the concept remains the same. The size of the blocks differs application, organization, requirement to requirement. But it gives me that ability. The paralleling gives me the ability to scale out, gives me the ability to add redundancy if it's required. And again, the strengths here are independent load sharing, where they're not communicating, and elimination of the single points of failure. When we get into smaller applications, this is a 10 kVA or a 20 kVA application, our tie point actually becomes a 12-pole distribution panel, where the UPSs feed into the panel, and the main bus of the panel is the tie point. How many people here have panels? Virtually everybody, right? When has a panel failed? Virtually never. That is your single point of failure on this system. No control module, no brains, no logic. It is as simple as it looks. And the KISS principle is paramount. So even on small things, we're using basically a panel as a tie point. So when we look at it from a capacity system, this system here as an example is 4 80 kVA systems. So really, from a power perspective, it's a 320 kVA power plant. capable of 320 kVA of power. And often when we deploy these type of systems, the loads will increase over time, and nobody really worries about it until you hit the capacity point, right? Until I exceed capacity, that's when people start looking at it. However, I do want to bring a point here in that in this particular example, if any UPS fails, you no longer have 320 kVA of capacity. So in fact, you have 4 opportunities of failure. It's better to have put in or to have a single 320 kVA of UPS than to have 480s here. Because you have 4 points of failure versus 1 in a 320 kVA standalone. So anytime you have a modular system, anytime you have a modular application or a modular design, you have to add the redundant module to reclaim or re-achieve the levels of reliability. Does that make sense? Same application, same configuration, but now the loads are only 200 kVA. Here I have redundancy. I can tolerate a failure with no critical impact. When one module fails, I now have a 240 kVA system. This is also called a 240 kVA N plus 1. Does that make sense? So you always, whenever you get into modular systems, you always want to have the plus 1 to achieve the redundancy. Another key point here. When we talk about distributed parallel systems, what we're really talking about is parallel runs. Right? We're talking about paralleling from point A to point B of multiple power paths. So when we're getting into this, we really need to be concerned about cable lengths and wiring lengths. And that's about the only real criteria that we really need to drive is from our incoming tie point to our outgoing tie point, the runs need to be the same. So the length of wire used from an input to module 1 and output of module 2 needs to equal input to module 2, output of module 2, and all the way through. So we touch base a little bit upon the primary challenge that we have, and that is when we talk about these systems and we talk about the scalability, and I'll draw, again, numerous examples here, but when we build these systems, by design, in many of them, we're operating in a 20 to 30% window. Take, for example, a scenario, AB. Is everyone familiar with AB or dual power path applications? Right? Many power supplies or computers or anything you purchase today will have 2 power cords on it, side A, side B. And it's redundant power supplies themselves. And the power supplies within that IT equipment or the processor are actually tied at the DC feeding into the printed circuit boards. So that's where you have a dual input power supplies or redundant power supplies. And the concept is, in that scenario, I'm going to put 2 power feeds coming in, or 2 power sources, side A and side B, and they're going to be redundant to another. So in that scenario, I would put 100 kVA on side A and 100 kVA on side B, and my load is 100 kVA. If any power supply fails, that 100 kVA, I'll go over to the other side. Does that make sense? So in that scenario, by design, the maximum load I put on A or B normally is 50 kVA, 50%. So by design, the maximum becomes 50%. Well, nobody wants to run at 100%, right? The traditional 20% derating factor comes into play. So really, optimally, my systems are running at 40% by design. Well, what does that do from an efficiency point of view? Really, really throws that out of whack. Likewise, with things moving around, I often find my operations operating in small designs. I did an application a long time ago, for one of the banks here in Mississauga. At the time, I think the loads were something on the order of about 200 kVA, but they were going to grow. And remember that how I started the presentation. We used our best guess at future growth, and we put in a 1.5 megawatt system. Right? They'll grow into it. They felt they'll grow into it. We felt they'd grow into it. So we built the infrastructure around 1.5 megawatt, figuring it would operate at a 1 megawatt N plus 1. So we took three 500 kVAs and we put them all together, and their loads subsequently went from 200 to 400 to 600 to 800, and then they went blade server technology, virtualization, and all of this, and the loads decreased. So I met up with them last year, and basically we had three 500 kVAs. Their actual load requirement was about 300 kilowatts, roughly. So on each one of these 500 kVAs, we had about 100 kilowatts, or about 20% loading on them. And the efficiency went down, because it was more of a traditional style UPS. The battery banks, let's not even go into there from a maintenance perspective on these systems. They were really just grossly oversized on it. So the question became, what do we want to do? And we seriously looked at, and economically it was almost there, of simply replacing that and putting in a 300 kVA. The cost of labor and doing all that almost equaled the operating cost of this large system grossly misapplied. However, they really, being prudent, they didn't want to, with the investment they had and the infrastructure they had and the familiarity they had, they didn't want to replace it with a whole new system. They wanted to make the old one work. So what we are doing now is every 4 months, in a planned, scheduled environment, we're actually turning off one of the modules. We're pulling it out of the circuit. So we start with module 3, we remove module 3. 4 months later, we're going to bring 3 back in, remove 2. So really what we're doing is, and the reason we're cycling them is for wear and tear and maintenance, and so they all get the proper recharge in batteries. But our estimates show that simply by doing that, by increasing the loads now to roughly 40% on each module, or 30% on each module, we're probably going to see about $250,000 savings over 10 years. Simply by manually going in there and doing that exercise to optimize the systems. Well, fast forward to today, and what are we doing today? How are we doing things differently? Well, for all the reasons that I just talked about, what we're doing today is when we're building a 550 kVA or an 820 kVA system, we're actually using internal power modules themselves inside the modules. So using today's technology, they are not going to be a 500 kVA block in each of these cases. It's actually going to be a 500 kVA, but it's going to be 150 kVA blocks. Power modules inside the UPS. Looks like a 550 kVA, smells like a 550 kVA, but when you peel the covers, it's actually 350 kVAs paralleled together within that cabinet. Well, why would you want to do that? Well, because now I can choose not to utilize 2 of those modules. Now that 550 kVA becomes 150 kVA. How complicated? About 1.6 milliseconds. Well, how do I bring it back on and make it back into it? About 1.6 milliseconds. So virtually instantaneously, that 550 can become 150, can become a 300, or can become a 500. Well, who chooses and how? It optimizes itself for the given application. So taking this live application, if it was with today's technology, I would simply not utilize 2/3 of each of the UPS systems. And it will automatically, every month, cycle through all the modules. What does that do? Well, it increases my efficiency now, not from 10 to 20, but upwards of 80 to 90% on the given module itself. I'm optimizing it on the fly. I look at that curve, it moves it from here to here. That's what we've done manually with that savings. Now I'm moving it out to here. Full optimization. Where does this really come in play as well? Well, we talked about virtualization, about loads moving around. I don't know when this particular client's going to decide to bring some loads over here on the fly, right? Maybe utility costs are more expensive somewhere else and not over here. Maybe organizational will move around. So they're constantly moving the loads around, moving it. So I don't know. This is a dynamic figure that can go anywhere upon that piece. I don't want to get penalized by building in the extra capacity, but I need the extra capacity. And so that's driven us towards this variable module management where you can move things around. And really, all I'm doing, again, it's very simple, right? There's a lot of math and logic and algorithms behind it, but it's really a simple concept. In this particular example, I've got a 550 kVA with two 275 kVA modules inside it. Normally, this is my efficiency curve. Right here, right? At 100% load or at 550 kVA, I'm operating around 94% efficient. And I carry that to about 40%, 50%, or about 200 kVA down to this point. And then my efficiency drops on a 550 kVA. By not utilizing one of the modules, this becomes my curve. This is now 275 kVA. This is now full load. This becomes my curve. So I program it that at 40% load, I simply disable one of the modules. Don't fire it. And again, I'm not turning it off. I'm not opening a breaker. It's still working. It's still synchronizing. It's still, ready to go beside it. It's just simply not doing it. It's the runner who's running beside the first person, waiting to jump in. Perfectly in sync, ready to be engaged. We're simply not firing the IGBTs on the inverter. So it's in a hot mode, ready to jump in. So we simply stop firing it, and we get this efficiency savings at the lower loads. When I take a 1.1 megawatt with all of these modules, it's accelerated in terms of my capabilities and what I can achieve. Also, in doing so, I don't need to worry about my increments. Remember we talked a little bit about the incremental? When do I choose the blocks and the different size blocks? This gives me a lot more versatility now in that I can now step in smaller increments by simply engaging 2 modules on the first system. So the discreteness of my steps allows me further to optimize for the given loads. Another real-life example. Client called us up and said, you know what, we want to build this data center. We're probably going to need about 825 kVA of power. That was the ultimate design. AB. So we designed it around 2 systems, 2 825 kVA systems. One on side A, one on side B to sustain this growth. Deployed it, installed it, put it in place. The actual load, not 825, never is. It was 440 kVA. AB, so it's evenly shared across A side and B side. So I had 220 kVA on each side. And remember, A is fully redundant to B. So if A fails for whatever reason, that whole 440 would go on to side, if B side failed, that whole 440 would go over to A side and continue operation. So that's where I have that full redundancy. Let's look at some numbers. Right? Again, remember, the 825 kVA is actually 3 modules of 275 combined together to support that load. Operating under this principle, 825 with 220 kVA, approximately 25% loaded, my efficiency of this system is 91.2%. And let's use that as the baseline. Now I start looking at it and analyzing it. My load is 440. It's split out evenly, so it's 220 kVA. Do I need an 825 kVA to support this? No. So I disable one of the modules. I don't utilize one of the modules. I now have a 550 kVA supporting 220 kVA. I've increased it now to 50% loading on my system. My efficiency increases to 92.8, and the real result, 56 megawatt hours per year of energy savings. that is not converted to heat, that does not need to be dissipated, that is hard cash savings. Have I given up any reliability? No. Have I given up any levels of redundancy? No, not really. But let's look at this even deeper. I have A redundant to B. Do I really need redundancy on A and redundancy on B? That's a lot of redundancy. Now, maybe I do. I don't know the application, right? We didn't talk about the application. Maybe it is a critical, ultra, super critical application and it requires 4 levels of redundancy. Maybe. Most people would look at that and say that's a little bit of overkill, as we did here. Maybe I can optimize it. So what I can do is for my 220 kVA, I can operate only 275 on that. I don't need 2 of the modules at this particular instant in time. At any time I might call them in, but at this particular instant, I don't need them. So I've got 275 here, 275 here, each supporting 220 for my total. In this scenario, 94.3 or 108 megawatt hours per year. Now, I'm not going to get into demand charges. I'm not going to get into kilowatt hours and taxes and all of the other parameters around that. But any value you use on that is significant. Now, how did we build these things and how do we distribute out of them? In this example, remember, and the principles are the same in many cases. It's simply the size of the blocks. In this example, I'm using a 12 kilowatt block, and I'm putting 6 of these UPSs together to get a 60 kilowatt N+1 system in this particular design. Same as the other blocks, same as the other drawings, but here, in this particular case, it's a 12 kilowatt 3-phase block capable and scalable to 60 kilowatts. So I often get the call, like, Joe, I've got this type of system. Can I add more power to it? Yeah, you can add a module, send the PO to so-and-so, right? No problem. I then get the call a few days, a week later saying, Joe, so I've added that module, but I don't have the capacity or the distribution on the output for that extra. Oops, right? Didn't think about that, right? Didn't ask the question. In that scenario, you're basically coming out of the parallel system, out of a modular system, and into a single tie point or a single distribution, be it an RPP, be it a PDU, be it a busway. But now you're coming out to a single system. So as you expand, as you grow, you might be limited by your distribution downstream. And as these things move around so significantly and so quickly, you run into these challenges. Now, think back here. Each of these UPSs is a standalone UPS system. As such, each of these UPSs has an output, right? When I use it as a standalone, it's got to have an output. When I combine them together in a parallel system, I'm kind of combining all of these outputs. So when I take these 6 UPSs and I now say you're part of one system, I also have 6 distribution outputs. So why don't I scale my distribution? Why tie it all back into a common panel? I can, but I suggest you don't do that. Start with a 12 kilowatts, add a rack of power equipment, add 12 kilowatts of distribution. Add a second rack, add a second 12 UPS, add more distribution. Add third, add more distribution. So you add distribution as you add power. The only thing you really need to be concerned about is having sufficient incoming power to drive your ultimate end game. And, as I had indicated, make sure you put the extra module in it to gain that redundancy back and the reliability back on it. So really, you have a power system made up of multiple UPSs. Deploy a multiple distribution path, a multiple distribution system along with it. Now, I also get the floor space, the physical space, by not requiring the extra distribution and the extra panels. So why do you want to go modular? Well, it's a pay-as-you-grow, right? I mean, I gain the reliability, gain the performance, but I don't have to pay for that oversizing or those fudge factors. And the requirements change. Nothing is static anymore. In fact, it's incredibly dynamic when we talk about virtualization and cloud computing and just networking in general. But also, what if the businesses move, right? The modular type of approach allows you to move around. In fact, more and more applications that I run into that where I would have put a 500 kVA or I would have put a large UPS in, I'm now putting 10 60 kilowatt UPSs, a UPS solution on the end of each row, because of the flexibility, because of the business savings versus the piece, versus any kind of an application. It's easier to deploy these at the time of use than necessarily pre-build a large data center.